now going to be talking about fluids. So off we go. Slideshow. We have a slideshow. That's weird. All right. So I designed this based on the textbook that you have. So as we talked about already, please make sure you're using the textbook, reading the textbook. All this stuff comes directly out of the textbook. You'll see a lot of the same pictures on here that you see in your textbook. Moving on. Let's talk about states of matter real quick. Okay. This is fluids. Fluid is specifically related to not just liquid, like normal people think. People would usually just kind of use them as synonyms. They are not. Fluids are liquid or gas. So we're going to be dealing with both liquids and gas and trying to talk about how we can do that. Now the goal of this chapter is not to rewrite the playbook. The goal is not to start from scratch. The goal is to use all the stuff that we've previously used, just make a couple of tweaks so that it's a little bit easier to measure. So let's talk about matter for real quick, okay? You talk about matter and states of matter over in chemistry, and you kind of get a little bit used to those ideas, but we can talk about them from a physics standpoint. If it helps for chemistry people in here, potentially taking Chem 2 right now, you might in chemistry call them van der Waals forces. We instead would talk about, let's just do this real quick, what are the four fundamental forces? Gravity, electromagnetism, strong and weak. What is gravity actually? Attraction between all masses. Okay. Strong holds the nucleus together. Protons and neutrons come to later level physics too, and we'll do that. Weak force has to do with like radiation, specifically one type. So what is electromagnetism? All right. So here's the best way to think of that. Okay. Inside a molecule, there are positives and positives and positives and positives. I'm going to ignore the neutrals right now. And of course, there's negatives all around the outside. And that is true of every single molecule up here. All right. So electromagnetism says, what are these negatives going to do to the other negatives? Repel. While those negatives are repelling those other negatives, they don't completely go away because at the same exact time, what are all these positives doing to the negatives over here? Attracting. So literally those two interactions mean that in essence, two molecules relatively close to each other are just wanting to get away and closer and getting away and closer. And essentially the bond is an invisible tug of war between these two forces. Like I said, chemistry people call these van der Waals forces in this particular guide. Now, let's talk about macro scale, which you already know to be the case. Let's use a material that you're very well intimate with all three phases. Let's use water. Okay, so let's start at a solid. When do you get a solid macro scale? When do you get, so what do you have to do? So what's up? You got to get the temperature, right? So let's talk temperature for a half a second real quick. We don't need it a ton in this chapter. We will if you get to thermodynamics later, but what is temperature? We've talked about it in here. What is temperature? What energy? Right, so you're right there. So what is that energy using physics stuff? Kinetic energy, correct. Temperature is the average kinetic energy of molecules. So you got 98 degrees and 102 degrees. What's the difference? The 102 degrees is molecules they're moving faster. Correct. You look at the equation 1/2 mv squared. Do you expect the mass of individual molecules are going to change in that process? No. So it is specifically their speed that is increasing. So how do we get from one phase to the other? Here it is. Okay. If they are cold, now, there is no 0 degrees Celsius no 0 degree temperature, absolute temperature here on Earth. Technically, it's absolutely impossible. We can talk why later on. Even 0 degrees Celsius is weirdly not a 0 because that's on the Kelvin scale. It's like 273. So that means that in solid, they are moving back and forth. Here are the molecules wiggling back and forth. But they're not wiggling very fast. So what are these things capable of doing? Pretty much holding them, relatively speaking, in place. They get solid. These are molecules where the molecules are not wiggling fast enough to break apart, or the forces are so strong that they can hold them very well in place. Make sense? All right, so what do you do to the liquid, what do you do to the ice then if you want to melt it? You add heat, you change its temperature, aka you give it energy so that the molecules do what? Speed up. The easiest way, by the way, is just choose another thing that is making them faster and faster. Like you take something over here and collide it with that so that these things speed up and the other one slows down. We can talk about that later. Point is, then what happens to these guys? They start wiggling faster and faster and faster, and eventually they wiggle so fast that these are still in place, but it's really, really hard to hold them in like one particular location, one particular area. They start wiggling around each other. So they're still going to be in that area, but they're not going to be like set in one spot, aka they've made a liquid. That's what a liquid is. The forces are strong enough that they're going to stay in that general area, but not so strong that they can't move around a little bit, unlike solids. And then finally, what do you do to get to a gas? Basically, you add so much freaking kinetic energy. This thing's moving back and forth so far that it, boom, this force cannot contain it anymore. It shoots that way too fast, and now it's independent entirely on its own, and there's your gas in a nutshell. Make sense? Okay. The main thing out of that, of course, to get in this particular chapter is that we know that both liquids and gas, fluids, okay, will not take up a definite shape. Fair? Okay. So, moving on. Gas. There's your gas. Circling around. Okay. Plasma, real quick. Plasma is basically just a gas, but it's charged. So, one is the main spot where you would go to get a plasma would be the sun. Because of the sun and the forces are there, the hydrogen and the helium regularly are charged. If you didn't know, alpha radiation regularly comes off the sun. Alpha radiation is a fancy word for it. It's just a helium. Literally just a helium that both electrons have been knocked off. And if both electrons are knocked off, you got two positives, no negative. It's a positive charge. It has charge. And therefore, we call it a plasma in that particular case as well. We get plasmas here on Earth, but that's probably one of the most popular right there. All right, let's talk density. Now, density by itself, not hard. Super easy equation, super plug and chug. The reason freaking why we use density, yeah, that gets a little bit more interesting. So what is density in a nutshell? Oh, by the way, a couple of things real quick up here just to highlight. Number one, looking at that triple line right there as opposed to an equal line simply means this. We, as humans, as scientists, as people pursuing this idea, defined it that way. We made it up. We 100% made it up. Okay, so when you do the equation, you're still welcome to use the equal sign because they are equal. They're just showing you that this is, in fact, is its definition. Okay, other things to mention here. Of course, obviously, when you're over in chemistry, you can use lowercase m too. By the way, capital M is just kind of used for an overall mass. Lowercase m is usually smaller masses. You'll get used to this as you go along. So we got mass over volume. When you were in chemistry, you usually use capital D because they're being nice to you over in chemistry and just making sure you make that association. We don't feel like you need that here. So we use the Greek letter. The more common science word is rho. If you don't know how to write it, it's basically a P with a squiggle on the end right there. What are the SI units? Well, what units do we typically use for mass? Kilograms. And what units do we usually use for distance? Meters, and therefore volume is typically going to be. Now, it's kind of funny, usually students to this particular point come across, whether I meant to or not, come across with a particular affinity towards SI units, and might even, if I asked you or pressed you, say that SI units are just straight up superior to their English counterparts at this point in time. Maybe you think that, maybe you don't. And the answer is sometimes yes, and sometimes invariably, like this conversation, it gets freaking annoying real darn fast. Because let me demonstrate real quick. That's a meter, yes? Okay, visual representation, the square that I'm making up right there, that is a meter squared. Okay, this is a cubic meter. That box, that square that I am, or that cube rather, that I'm creating right there, it's a gigantic freaking amount of space. Yes? Here is 1 kilogram. 1 kilogram, just remind me once again, what is the definition of mass? My terrible definition, technically. Amount of atoms that take up an object. So obviously this would be more dense because we're going to get a lot more atoms inside this. But actually, roughly speaking, actually that's interesting. I never thought of this before. It's kind of close. The amount of atoms in this for air, roughly about the same. Same amount of atoms in that cubic amount of space. Not quite, you'll see in just a minute what it actually is, but pretty darn close in this particular case. Obviously, this would be, the air would be less dense because same amount of mass, but I know it's weird. Yeah, different volume, larger volume. As a matter of fact, we can talk about that in just a second. So, the standard units are kilograms, meters, cubed. But I'm going to be honest with you, those units are freaking annoying. Okay, specifically because I'm going to be dealing with objects that are like this size. Is this a cubic meter? I hate fractions. Okay, as I imagine you do too. So what does chemistry do to avoid the fractions? They use two other units. What units does chemistry typically use instead? Grams per centimeter cubed. And the beautiful thing about chemistry and the way they handle that is that density and water are intimately related. As a matter of fact, okay, certain values were decided simply based on water and this next number. For water, 1 centimeter cubed is 1 gram. That's the density of water, which is incredible, but we don't often think about what that actually means. That means if I go to the back, oh, by the way, I want to say that I want to use this a second ago and I realized it. So you know the easier one than centimeter cube, what we start to use because we don't want to write cubed all the time? Centimeter cubed is a milliliter. Right, so if you hear milliliters, that is a centimeter cubed straight up 1-to-1. That's just by definition how it works. So I go to the back, I grab a graduated cylinder, and I fill it up with water till it has 74 milliliters. Now that 74 milliliters could take a ridiculous amount of shapes. Yes, not just a column, but all over the freaking place. It could take up this amount of space. Could take up, it's going to fill the space. I could fill this thing with it. It would be all over the place. But the beautiful thing is that it's 74 milliliters. It has a mass of 74 grams. Right? Here's the true beauty of density. We don't give a crap about density. But what we really want is mass. Why do we want mass? Because we know all the rules already. If you have mass, how do you find weight of an object? Multiply by g. If you have mass, how does its inertia work? Sum of forces equals ma. I want to use all the rules I previously did. But if I just poured a bunch of my coffee out on the table, could you measure the mass very easily? No, you couldn't measure the mass very easily. That being said, what could you probably measure relatively easily about a liquid? The volume. And with volume, along with density, you could easily get mass. As a matter of fact, this is its definition, but a little bit of algebra later, this is more often what you're probably going to use. Multiply V on both sides. Mass is just equal to density times volume. I did this just a second ago with water. I said, hey, if I have 74 grams, the density is 1. Boom, the mass is obviously 74 grams in that particular case, yes? Let's try it again. Earlier this year, you might remember that I said something to the effect of I was talking about the air in this room. And I said, how heavy do you believe the air in this room actually is? I think usually, because I asked that question, they pick bigger numbers than they would have otherwise. A lot of times people just kind of going into it go, oh, air is real ridiculously light. It's like a half a pound or whatever. And I said it was a little bit more than 1,000 pounds, right? Oh, okay. No question here about how I freaking got that, right? So let's talk real quick about how I freaking got that. Number one, I roughly estimated the volume of this room. You know the volume equations from geometry. You got your base times width times height. You got your 4/3 pi r cubed. You got your pi r squared times the height if you got a cylinder, your basic shapes, yes? So let's treat this room like a box. Top to bottom, I've mentioned before that it's about 3 meters. Side to side, I measured this earlier, roughly about, I think it's like 28-ish feet. So let's go about 8 meters in that particular front. So we're at 24 meters squared on that particular front. Front to back is about 47-ish meters. Let's say, no, sorry, 47 meters. That's not great. 47 feet. Okay, so like 15-ish meters, probably less than that. So let's go 12. So I just did 3 times 8 times 12. Is that right? I did earlier. I did numbers differently earlier. Yeah, I definitely did. That's okay. So 3 times 8 times 12. About 299 meters cubed roughly in this room. Yes? Cool beans. Now, what do? Air. Air has 1.29 kilograms for every meter cubed. So I just learned there's 288 meters cubed, so I just multiply by 1.29. And now I know that the amount of mass in this room is about 371.5 kilograms. You mentioned this a second ago. If I want to know the weight now of all the air in the room, what very simple thing do I do with kilograms? Multiply by 9.8. So it's 3,640 newtons. And if I wanted to know what that was in pounds, I would divide by 4.45, and I get about 818. I think I usually say about 1,000 pounds somewhere in here, but there you go. That's how you do it. Again, what do we want to do with volume and fluids and liquids? Ultimately, the answer is we want to just use the same rules that we always have. But that's easier to measure in general than that, right? What would I have had to do to figure the mass of everything in this room? How the freaking heck am I going to put that thing on a scale? But to take all of the mass and combine it into one particular area and set it on it, that would be ridiculously annoying. Way easier in this case to measure the volume, right? Same thing is true of any sort of liquid in a weird shaped container. I don't know, quickly I don't have a geometric shape, but I could pour this into an easy geometric shape, figure out what its volume is, and then once again, just use regular density in order to go from there. Does that make sense? Cool beans. Let's move on. Yes?
Well, writing and solving equations, do we need to use the three
I said earlier, no, you definitely don't need to. Equals is completely fine in this case. Again, all that says when you write that up there is that we defined it, we made it. This is not a fundamental thing. So to the counterpart to that, if you were looking at these slides, if I had been using these slides when doing like Newton's second law, it would straight up say sum of forces equals ma, and we would use that because we did not decide that. That is the law. That is the way that things work right here in this particular case. All right, a couple other things real quick because we're going to use it all the time. You will notice that I said this earlier. Which one should I use, Spainhour? If I'm doing this, well, I'll tell you what I would do in a lab. I'm using these numbers. I'm absolutely using these numbers. Why? They're way easier, and they're not going to be ridiculously tiny fractions, right? If I wanted to do this guy in centimeters cubed, I would treat it like a cylinder. I would go, well, that's about 7.5, so half of that is 3.75. Find the area of the circle, 3.75 squared times pi. So the area of the top is about 44 centimeters cubed. And then I would go down, I get 25 centimeters, so times 25. I got 1,104 centimeters cubed, and I can get a sense that that's about a little bit more than 1,000 milliliters, or actually a little bit more than a liter, right? A liter is about 1.1 liter. That's about half of a 2-liter bottle. I have a whole bunch of context by doing that. If I wanted to do that exact same conversation in meters, I would have done this. 0.35 meters squared times pi times 0.25 meters, and you would get the same type of thing with 0.035 squared times pi times 0.25, and you'd end up with this freaking number, 0.000962, or I think roughly, actually, if I give the numbers that I did earlier, 1103 meters cubed. Would you rather use 1,100 centimeters cubed or that in meters cubed? Probably, yeah, I would say absolutely centimeters cubed. So let's talk about conversions real quick because there is a weird that sometimes people don't get enough practice with. Let's talk about this real fast. Let's convert what this is to meters cubed. Let's actually put this guy over here. This is 1 gram per milliliter. All I'm doing right now is converting this to our standard set of units. So to do that, let's go ahead and put grams on the bottom because I want to cancel grams, right? Just canceling my units. So that's not equal. That should be multiplied by. Kilograms on top. What's my conversion between the two of those? It's 1,000 grams. Next, centimeters cubed to meters cubed gets a little wonky. So let me give you a visual representation of the math therein. You probably know the rules, but you might not have always associated the math. How many centimeters in a meter? 100. Of course there are. So how many centimeters squared in a meter squared? Well, there's 100 on this first line. And then there's 100 on the second line. And then there's 100 on the third. And how many lines are there? How many lines of centimeters are there going to be up and down now? 100. So you have 100, but 100 lines. So that means that's 100 squared, or 10,000. Right? Now, there's 10,000 centimeters squared in that. How many lines of that 10,000 are there if you go out to a cubic now? Another 100. So if you think about the math on that, what was it really? It was 100 times 100 times 100. In other words, there's the concept. Here's the easier way to do the math. What you do is you line up the units with the linear variable, but just listen to this carefully. The linear and the cubic cannot ever convert the same way, but you can start with the linear. What is the conversion here between meters and centimeters? 100 to 1. And then the very simple thing that you can do, but you have to remember to do this, is cube everything. If I cube centimeters and I cube meters, then I would technically cube the 1, albeit that that's just 1, and then I cube the 100 on top. 100 cubed is 1 million centimeters cubed. And so if I do this conversion, you'll see that 1 gram per centimeter cubed, I got 1,000 on the bottom, 1 million on top, actually gets to, what's my conversion number? 1,000 kilograms per meter cubed. So, what does that number mean? What does it mean that water has 1,000 kilograms per meter cubed? Visualize this. So what does that mean is the case?
In that cubic meter, there's 1,000 kilograms.
If this is full of
water,
and it takes up a cubic meter, then it will have 1,000 kilograms. Now there is an assumption of temperature there, there's an assumption of pressure there that we'll talk about as well, but for right now, at our standard units right here, you can assume that in this classroom, if I had a cubic meter of water, that it would be 1,000 kilograms, and therefore weigh 9,800 newtons. Or, roughly speaking, a kilogram of water, 800 newtons, what is that maybe? Doing my math right, 1,000 times 9.8. And I'm going to divide by 4.45. A cubic weighs a little bit more than a ton. 2,202 pounds in that particular case. One of the greatest sources of mass if you just needed the mass for mass sake. But again, why are we doing it? Because what we really want is mass, so we can use that for gravity and use that for thing. How we do it? Okay, a couple things to point out real quick that are important on this. You'll notice that all of your units right up here are in kilograms per meters cubed. Okay? But another very important distinction, and the reason why they do this to help you out is this. You will notice that there is all of these guys right over here, all of these are solids, and all of these have a times 10 to the third right over here. Yes, they didn't write them all the way out. Why do they have times 10 to the third? Because times 10 to the third is 1,000. So if you want to know these same densities in gram per milliliter, because of this conversion I just showed you, by the way, you are also welcome to use this particular conversion. You don't have to do this work in between. I've done it for you already. Okay? What is the simple thing if I said, hey guys, what's the density, say, of silver in grams per centimeter cubed? Well, all you do is just take this off because you just divide by 1,000, and the answer would be 10.5 grams per centimeter cubed, right? Of course, if it is kilograms per meters cubed, if you need that. So then the question becomes, okay, Expander, you said you're going to use grams and centimeters when you're in a lab. Yes, 110%. That's exactly what I'm going to use. So why the heck are we doing these? Why on earth are we doing these whatsoever? And the answer is, because if I use Fg equals mg, what is the assumption of mass in that particular case so that you get newtons? It has to be in kilograms. So if you want to use those standard equations that we've been using, it does have to be in kilograms in this particular case. Why do we not talk about density of humans very much? Why have we not talked about my density to this particular point? Well, that's true, but that's not, I'm mostly liquid. We probably consider me mostly a solid. All humans pretty much a solid. As such, is it that hard to measure straight up what my mass is? So we don't really need to worry about density because we don't really care about density. Like I said, what we care about is mass, and we can skip to the end in that case. Whereas fluids is not as easy to do. Yes? Let's move on. All right. Fun conversation. We can make it more interesting. Let's talk pressure. Pressure is a harder one. Okay? It's going to be harder because you probably messed around with density before. You might even thought some of these exact same thoughts. Before pressure, you probably haven't thought of very much. Now, the great news is that if you understand, this is why, by the way, you might have, oh, why do you freaking take so long on density? We get it already. The answer is because pressure is the same freaking conversation. What is pressure? Well, let's talk about this real quick. What is atmospheric pressure in this room? My chemistry people would look at me very quickly and go, 1 atmo. I'm good, right? Or yeah, just get 1. That's all I read. Or if you want, does anybody have it up? Come on, chemistry. What is atmospheric pressure off the top of your head? What you got? You know? All right, fine. Look it up.
14 psi.
What's that?
So like 14
Okay, so interesting on PSI, because I was actually I thought you would probably hit the other one first. You're fine. You're completely fine. I was gonna ask that 1 second. If you hadn't done that, usually people give me, after looking it up, the other one. What's that? Just thought this was on the side. So look it up if you don't already. Don't wait for other people to look it up. I need several people to look it up. Come on, yeah, atmospheric pressure. What's that?
101 kPa.
All right, so let's talk 101 kPa. Pressure in by definition, again, you'll see that triple line right there. Pressure by definition is force per unit area. Okay? If you want a picture, here it is. Okay? In this room, there's a bunch of air. Yes? Hopefully. What is that air currently doing to this board? Running into it. Yes, now, if you're not paying attention, obviously it's doing that to both sides. So I don't really have to worry about one side being a higher pressure than the other. By the way, what does it feel like in a room, naturally, if one pressure is greater than the other? Don't think about this more complicated than you need to. What's that? Wind, yes. Because if there was more pressure over here than over here, what's it going to do? That means there's going to be more force. And if there's more force this way than that way, we just have Newton's first and second law again. If there's more force that way, then what do things do? Accelerate that way, aka wind. So when there is no wind in the room, when you don't feel any push one way or the other, what can you be certain about the pressure? It's equal. So let's talk about what PSI and all that sort of fun jazz is. If you use standard units, what units do we use for force? A Newton. And this is a little bit annoying. It's not on purpose, but is a Newton big, small, what? It's ridiculously small. If you remember, a pound is 4.45 newtons, and thus a newton is a little bit over a fifth of a pound. So 0.23, something like that. Pound's not very much whatsoever. On the opposite freaking end of the spectrum, here's a square meter. So is air probably going to be able to put out a ridiculous amount of newtons in this square meter? Yes. How many newtons can it put in a square meter? 101,300 newtons in 1 square meter. It's a gigantic freaking number. But the reason it's such a big number is partially because that's a gigantic area, right? So weirdly, this is one of those cases, again, where it probably makes more sense to understand the concept using actually English units, not the other. Let's talk PSI. What does PSI stand for? So instead of newtons, we use pounds, and instead of a meter squared, you use roughly a square inch. Okay? There it is. Now, this is a little bit bigger, by the way. I estimated earlier, and then I measured it afterwards, so it should be a little bit smaller, and it's not important. So what does that mean, 14 PSI? It means on this square inch of skin, air is pressing on me right now with 14 pounds. Now, if you think about that logically for a second, that's going to feel a little weird, because this, unfortunately, later, this guy right here, sorry people online, it's a 10 pound. That's 10 pounds. 4 more of those are sitting on every inch you have of skin. What's that? 14.4, yeah, 14.4, yeah, it's 14. 14 pounds. I said 4 more is what I said. 4 more than 10.
Oh.
10 pounds. This is sitting on this, plus 4 more pounds is sitting on every square freaking inch of your skin. So yes, this inch, but also that one, and 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 let's say roughly, I don't know, I'm kind of just estimating here that my arm takes up, let's go, 25 square inches. That means freaking on my arm right now, my calculator here. So we got 14 times, oh there we go. 14 times, what did I say, 28? What did I say? 24. There's 336 freaking pounds sitting on just my forearm. That's not to count the back of my arm or my torso. That feels a little odd, yes? Okay, so the question that you might have is why don't the heck we feel that? And the answer is twofold. Number one, you have a skeletal system. Inside that skeletal system, you also have liquid inside your body. What you don't understand is that, yes, air is pressing in with 14 pounds per square inch. But look at my skin right now. Is it going anywhere because of that air? So that means it's following Newton's first law. And Newton's first law means forces are equal. So that means 14 pounds are pressing that way on the lid, but guess what the liquid inside my body is doing? Pressing out with 14 pounds. We forget to talk about both of them, okay? So where is this particularly important? Let's start talking about space for a second, okay? And the reasons why you die in space, okay? By the way, do not trust Marvel, okay? Don't trust Marvel in this particular case. This particular conversation, I'm going to begin with a dumb joke. It's not meant to be funny. It's meant to help you remember physics doesn't suck. It does suck the way you were just thinking. It doesn't suck in the form of suck, okay? When you think of suck, you think like a vacuum. In a vacuum, what you think of is like, okay, here's your vacuum. Here, this represents the vacuum. The coffee I just left out. Okay, here's the bottom of the vacuum. Okay, which way do you think the force is? What do most people think which way the force is going when you use a vacuum? And go that way. So they naturally assume that means something is pulling that way, and they say that there is a suck in that case, and that is not true. There is nothing that is pulling that way. Here's what's actually happening. What's actually happening is that when the vacuum isn't on, there is air inside the vacuum. And the air outside the vacuum is pushing in with 14 pounds per square inch. But the air inside the vacuum is pressing out with 14 pounds per square inch. And so the net force is 0. So you turn the vacuum on. And what does the vacuum do? It takes out the air. And if there's no air in here, if there is no air in here, then there's 14 pounds pressing inward. But is there anything pushing out anymore? And therefore, force goes in. That's what's meant by saying physics doesn't suck, it only pushes. Okay? So think about space. What happens to a human when you throw them out in space? We don't talk about blood boiling and that whole triple point. What's that? Sure. Does anybody know like what you would do, kind of what your body would do immediately, assuming that you're not in, sort of. But essentially, yes, that is correct. You would blow up, or let's just like literally, you would look like a balloon. Yeah. Okay. Why? Well, we just said it a second ago. What's pressing inward on me right now? Air. 14 pounds per square inch. So what's the inside of my body doing? Pushing out 14 pounds per square inch. What's the defining factor of space? There's nothing out here. So is anything pushing in? But is my skin still pushing out at 14 pounds? So it's actually not space that kills you. It's you that kills you in space. Just pressing outward in that particular case. Let's use an easier example. You go up to, you drive up to Colorado. You start to drive up into the mountains. As you start to drive up into the mountains, what gets a little bit annoying? Specifically, your ears, the pressure on your ears. The reason why is there is a tiny little piece of material in your ear called the eardrum. Okay, and standard, when you're sitting right here, guess how much pressure is pushing inward? 14. Guess what's pressing this way? 14. Then you go up into Denver. What changes when you're up in Denver? There's less air. And since there's less air, I'm going to get to this in just a second. What is pressure actually? Actually, we're not going to go to that. I'm going to make a quick aside. I'll come back to this example. Okay. In a nutshell, here's what pressure actually is. Some material, air running in, pushing off. Air is running in, pushing off. It's collisions in a nutshell. You want to get a good sense of what pressure is? After class, let me know. And you'll stand there and I'll just keep running into you and doing off. And I'll run into you again, coming off. Now, obviously, you don't need to worry about me. You can measure force because there's one of me. But there are literally trillions upon trillions of air molecules. Are we going to try to keep track of every single one of those forces? No. So what we do is we average it out and we look how much force is happening in a square inch. Now here's a good question. Why are we using pressure and not just straight up using force? Well, watch this. I'm going to draw a box on the board. Okay? There's atmospheric pressure on that box. Yes? Yeah. If I double the area, what changes and what doesn't in this equation? The volume. Well, we're not volume right now. We've changed area, right? Literally said I doubled the area. So what in turn changes? The force. Why has the force changed? Because I doubled the area.
There's more surface area.
Twice as many molecules running into that. Now, are the molecules relatively evenly spaced out? See previous conversation on density. Is the density pretty much the same of all the air molecules everywhere in this room? Yes. So if I double the area, what do I just expect about the collisions? It doubles. But if the force doubles, because the area doubled, what didn't change? The pressure. So ultimately, what we really want to do is we really want to have a conversation about force, right? But that's hard with air, so instead we have a conversation about pressure. And in area and in situations, going back to that example, where am I at on time? Okay, cool, good. Okay, in the eardrum, what's true of the area on the outside and the inside of the ear? What is true of the area outside versus the area inside of the ear? That should be exactly the same on both sides. So, really want to have a conversation about force, but I can have the same conversation in this case on pressure in this particular case, which is going to be the same for everywhere. But watch this. Is the force on my eardrum the same as the force on my forearm? No, look here. Look at the difference. Think of this conversation before. Here's the eardrum. Smaller area. So is the force the same here versus here? Is the pressure exactly the same here and here? Yeah, so we can have this conversation, the pressure where it stays exactly the same, even though we ultimately want to talk about force, right? So, going back to the eardrum conversation, this will represent the inside of the human's head, and this will represent the outside of the human's head. Okay? What happens is there's less air out here. So what happens to the number of collisions? It's less. So technically what happens to the pressure out here? It gets less. So since the pressure out here is less, then that means given the same area, there's greater force that way than there is that way, and that stretches your eardrum, and obviously that hurts. So all of you have a tube inside your head that directly connects the inside of the eardrum to the outside. It's something, I can't remember what the name is. People with potential ear problems might know this. It starts with an E. I can't remember what it is. Point is, there's a tube that simply opens, and what it does is it lets air out or lets air in, such that, guess which way the air is going to go if the pressure inside your head is bigger than outside? It's probably going to push out. And so what's going to happen to the amount of air in your head? It's going to go down. So what's going to happen to the pressure inside your head? It's going to go down until they're equal on both sides. Now, the easiest way for you to open that tube, if you didn't know this already, and you already know that, is to swallow. Okay? You can also force air out. That can be a little bit dangerous. So the easy thing is usually chew gum, because you're regularly swallowing in that particular case, or eat some food that opens that tube regularly, assuming that you don't have any ear issues, like people with perennial ear issues. All right. So, again, why do we use pressure? Let's actually do one more example real quick, because maybe this will help. Okay, here's a balloon. I put air inside that balloon. Yes? Mm-hmm. Why does the balloon stop moving outwards? Or why did it move outwards? What happened? No, not yet. Don't get to that first. Don't start with that. I put more molecules inside. So if I had kept it the same volume, what would happen to the density of the molecules inside? It would increase, which would mean the number of collisions would increase, and therefore, there you go now. That means the pressure on the inside is greater, and it's the same area outside as inside. So if the pressure on the inside is greater, that means the net force is pushing out. And so what happens to the surface? It goes out and out and out and out. When does it stop going outwards? When the forces inside are equal to the forces outside. But why do I want to talk about forces? Why won't I? The pressures are also equal. So let's watch this. I'm going to put more air in. Compared to the earlier volume, the force on this balloon is now greater or smaller? Greater, because?
Adding more area.
But, and this is why we want to talk about pressure instead. The forces are equal on both sides. I know because the net force is zero. I know the net force is zero because it's not moving anywhere. Forces are balanced. But the forces now, compared to the forces earlier, are bigger because the area is bigger. So doesn't it make more sense to say that the pressure in this case is balanced on both sides? Equal pressure per square inch, equal pressure per square inch, equal pressure per square inch. In that case, even though the forces, and you can, by the way, feel this with the balloon. That's cool. I didn't even realize this until I was just doing this. it takes more force for my fingers to keep this closed when the balloon is open, because there's more force in that case, than when it's closed. There is less force right now, even though the pressure in all three cases were exactly the same. Yes? All right. So in that situation, watch this, was pressure stays the same, so you just watch these two change each other. But here's another instance. You ever step on a nail?
Nope.
Yes,
I have.
Hopefully no. If you have, you know what happens. Obviously, more than likely, your foot goes in the nail. Okay? Because you have a certain amount of force. And there is a tiny amount of area in that particular case. But maybe you probably know this or don't. What happened? Can you sleep on a bed of nails? Because if you go from the nail to the bed of nails, does this number change? No, the weight of the person doesn't change. What does change? The area. And as such, as the area gets bigger, the pressure gets less in that case, thus making every individual part on your skin not have to push with as much force independently itself. Last example on this is here. Again, you can see it here by just leaning your entire hand on the table. Pretty easy to do. But if I attempt to do the exact same thing but only hold myself up by one knuckle, I'm going to be in a lot of pain in this particular spot because this particular location requires a lot more force because it has so much less area in that case, aka we would say its pressure is incredibly high in that particular spot. Okay. Last thing to cover real quick is atmospheric pressure I started talking PSI. Similar to the conversation earlier, you can see why I was talking PSI colloquially, because it's easier to understand in a small thing. But the problem, of course, is coming back here. Ultimately, we said which of the three of these is the most important, the one I actually want to deal with. Force. Why? Because we already got rules for it. I want to do those rules. And force is defined as kilograms times meters per second squared. The area, of course, is in meters squared. So the units are newtons per meter squared, otherwise known as a Pascal. A Pascal is just a newtons per meter squared. When do I have to use it? Well, you have to use it if you want to get out newtons in this particular case. So 1 atmo is 1 atmosphere, also known as 14 psi, that is 14 pounds per square inch, and that is the same as 1.013 times 10 to the 5th pascals. Let's talk about that number real quick in a minute so that you can understand how to see it and use it that much more efficiently. I don't like writing this all the way out. Also, the 3 on this is the 4th significant figure. I personally regularly drop it. You're welcome to do the same. Times 10 to the 5th, I don't want to write that out all the time. I also don't want to write out the full number. 101,000 pascals. Because I just don't want to write a bunch of extra zeros, so I'm going to be lame. Here's what you can do to be lame as well. Now I have to use this number, in this calculation. This is the number you got to use. But so that I don't have to write it as much, is this the same thing? Yeah, that would be just as annoying as writing that, arguably worse, except there is an SI unit that is already in place to use times 10 to the 3rd. What SI unit do we have? So, instead of write times 10 to the 3rd, you write kilo. 101 kilopascals is what I regularly write in my equations, but the thing you got to know is when you punch that in your calculator, you don't write 101. You either write this, or you write 101 times 10 to the 3rd when making that calculation. Start the homework as early as you possibly can, because it will help. Guarantee you. I would do a problem or two tonight. That is best practice. And the great news is, if you have it figured out, it's easy. And if you don't have it figured out, now you know.